So where'd you find Parker? Parker in shoes. What? Parker in shoes.
Good evening, everyone. Start right on time. Good evening, everyone. Welcome. Special welcome to Dr. Sam Schacher. Welcome to the Monday night Resident Scholar Series. It's a pleasure to have you. Dr. Schacher may not need an introduction for us here, since we all know him from the Shkama Minyan. But for all those viewers on YouTube, Dr. Schacher, his resume is obviously very impressive. Dr. Schacher is the professor of neuroscience at the Columbia University Medical Center, as well as the New York State Psychiatric Institute. Dr. Schacher has done a lot of work on the areas of learning and memory in neuroscience. He also runs a course at the Columbia University Medical Center for medical students on neural science as well. Tonight, Dr. Schacher will be beginning his lectures on the neurobiology of free will. Tonight's class, background, and brain organization. Dr. Schacher.
Hopefully you will applaud afterwards today. All right, thank you. Thank you for the introduction. Thank you for coming out tonight. As you can see on the slide, I'm going to be talking about the neuroscience or neurobiology of free will. And this topic came to mind. Some of you probably heard me jabbering away about this over the course of the past year or so. Through a confluence of seminars and reading reviews and a book by a radical atheist, Sam Harris, on free will, and then a series of lectures at a department by prospective new hires by our department, people who are studying the decision making both in an economic setting, how humans and their brain activity induce economic decisions, taking risks or going for a sure bet, for example, differences in brain activity as a result of that. And those seminars were given by Antonio Rangel from Caltech, and a series of seminars by Michael Shadlin from University of Washington, Seattle, on decision-making, motivated decision-making, both by humans and primates. And it pointed out to me that the degree of information about our understanding of the brain and human behavior has reached a point where we can now begin to address how brain activity leads to specific decisions. And people have begun to study that. And the initial interpretation of those experiments are not such good news in terms of those who feel that there is free will. And in fact, the preponderance of the interpretation, I'm not going to say the preponderance of the evidence, has been that we have relatively little free will based on their interpretation of the data. That did not sit well with me when I first read it and heard it. So I began a year-long delve into this area. I am not a philosopher, so I am not going to get into the discussion of the philosophy of free will. It's been a discussion that's been going on now for 3,000 years, plus or minus a few hundred years. There are important religious thinkers on the issue of free will. The topic of free will is covered in the Torah and Tanakh, in Chazal, in medieval philosophers. But it's really only in the last 120 years or so where the science of the brain has been established to a degree where philosophers have to now take that into account in making their discussions about how individuals, whether they have free will, how much free will they have, etc. Now, from the point of view of society, it's not a big issue. Society can define what free will is and responsibility is in order for society to exist. That's a practical issue. But from a religious point of view, for example, and for the understanding of how the brain works in general, it's important to understand the contributions that brain activity has on our capacity to make decisions. So what I'm going to then do today is cover this set of top
There we go.
Turn.
All right, so what I'm going to then be discussing today is some definitions about what free will is from the context of how neuroscience would then interact with behavior and contribute to free will. And in the second and third lectures, give concrete examples of the evidence in a sort of a very selective kind of way, the evidence that one can bring to bear to support one side versus the other. And during the course of that, I'll then contribute my own personal hypotheses, if you will, and interpretations of the data, and how it then can inform us of how the brain can contribute to free will. So let's have some definitions. I have some selected quotes from William James here, and we want to define, at least from how a neurobiologist may approach the problem of free will, and I'm using the definition of free will that some more contemporary philosophers, John Searle and Thomas Nagel, have used to define some of the key features of what free will will consist of. Now, some of these definitions are very commonsensical. In order to have to commit an act of responsibility, of free will, the individual has to be conscious that they can't be asleep, they can't be anesthetized. Although there are Freudian interpretations that most of the things that motivate us are subconscious, that idea is not completely validated by modern evidence, but that's not really important for this regard. What's important is that the individual has to be conscious. Now, the definition of conscious that a neurobiologist can now design experiments and test, and I think cover more or less the key features of what an act of free will would entail. The individual has to be self-aware. That's a sort of an open-ended statement about what that might mean. But its simplest interpretation is that one realizes that one has boundaries, that one interacts with the environment and the rest of the world, and therefore can interact in a subjective experience kind of way. So one can interact with both internal and external stimuli in order to initiate and respond appropriately to specific behaviors. And then the last component of that free will act is that you're informed of the various possibilities when you in fact intend to do that act. So the act of a free will then has two components. It's the free part, where you can select among a variety of choices in terms of actions, what you might want to do. All right, and then the execution of that act. And remember, an act of free will includes both will and won't. So it covers both the Judaic and Christian values of the golden rule, which is we either do unto others that we would want others to do unto you, so that's a positive act. And then Rabbi Akiva's, or Hillel's comment of don't do unto others that you wouldn't want them to do unto you. Now, selecting a negative act, a passive act, there are many ways in which one cannot do something, right? I mean, say you're deciding about whether you want to vote in the past election, and you say, both of these candidates, they're silly and they're not worth voting for. So I decide I have a choice to vote or not vote, right? And I freely make one and say I'm not going to vote. How am I going to not vote for those candidates? Well, I can go to work, I can stay home, I can go to the movies. I mean, there are almost an infinite number of ways in which one can execute a don't. And in fact, most of our moral decisions are in fact don'ts. How does a neurobiologist study a don't? It's very complicated, since one has to time lock brain activity with some action, since not doing something cannot be time locked to any particular event. It's very difficult then to correlate or relate specific brain activity to not doing something. So it puts restraints on what a scientist can actually study, and that is, of course, an important caveat in all of the data that I'm going to present to you, in that it cannot take into account significant realms of decision-making, because it just can't study those specific types of things. But neuroscience has to take all of these issues into account in order to come up with an overall understanding of how the brain performs an act of free will. Now, most people here would admit that an act of free will is committed by the brain, right? It's done by the brain. The question that one has to address is it the only part of existence that contributes to an act of free will? So this is, again, a discussion that philosophers have dealt with over thousands of years about the issue of the dualistic aspect of what is responsible for the mind. Is the mind something other than the brain, or is it accounted for completely by the brain? Well, I am a card-carrying neurobiologist, so I already have my biases with respect to this, but that bias is supported by a preponderance of the evidence that would indicate that the brain is completely responsible for the mind. In other words, the mental is the physical, and there is no other component responsible for that. And this idea, of course, was first elaborated by Santiago Ramon y Cajal, who is the Saba Raba of neuroscience. He won a Nobel Prize in 1906, one of the first prizes in physiology and medicine. And he basically, was like, Torah Kula on Regel Achat. He was able to, through observation, come up with ideas that are still correct today, and is the driving force for much of what we know about how the brain works. And he already, by his observations, came to the conclusion that the brain is it, in terms of what the mind is capable of. And what I've added to that in a 21st century kind of way is that the mind is an emergent property of the wiring of the nervous system. And what I mean by an emergent property is that it is not completely explained by the ways that the functionality of the individual parts, and that it has something unique about its features as a result of the complexity of the brain, and that complexity and that emergent property still needs to be discovered, but it's a fundamental hypothesis of modern neuroscience. And that mind and those circuits are then modulated continuously by the genes, the molecular complement that the cells have at a given time in the life of the organism, and the environment that then acts on those genes, mediated by the molecular complement within the cell. So the point is that the brain is not a static unit. It is a continuously modulated organ that is undergoing continuous change as a result of the experiences that the individual has, and that those changes therefore result in the subjective aspects of the individual, and that subjectivity therefore leads to a significant degree of indeterminism to how the human behavior can then manifest itself at any given time after that. So that one could not use a deterministic explanation, which is the opposite of free will. In other words, you do things exactly because of the following sets of causes that the physical nature has in mind. But it is different for the nervous system because of this emergent property that allows it to express itself in ways that are unpredictable. So the brain is therefore the biological basis of the mind. But one of the things that happens to the brain, as we always say, is that with age, for example, you cannot teach an old dog new tricks. That's not really true because the number of tricks that one can learn is almost infinite, and since many of those tricks are learned at an earlier stage, you sort of get used to the idea that, I've learned it all, but in fact your brain is changing all the time. However, as William James pointed out over 120 years ago, we're capable of training the brain during certain periods of time, most likely, typically in one's youth, where one can then learn lots of things, and he sort of recommends that the young should realize that they should learn whatever they have to learn now, or soon they'll just be a person of habit and no longer capable of learning virtue, which is what his point was. And that second quote that I have from William James, I thought was wonderful because it's one of the few sentences that one can find where there are 3 double negatives. And I find that to be, perhaps they were paid by the word in those days. But I think the point there is something that Chazal and Judaism, Rabbinic Judaism, has been talking about for centuries, which is that one, by just pure repetition of doing virtuous acts, one becomes virtuous, and then the virtue becomes habitual, and thus society lives happily ever after because of that. It does take away a little bit from the concept of free will, because if you're doing things out of habit and rote and not really being cognitively aware of that, it sort of reduces that free will. But as one of the points that I'll be making in the third lecture is that idea of training individuals and being virtuous and ethical may in fact be an important component of our education system, because we seem to leave that component out. And it may be useful to have courses, real courses in high school, for example, in moral dilemmas and having the students figure out how to get around that. But the whole point of this is that in spite of the fact that there are critical periods in which one learns something and is effective in learning that, and then that then stands up to time in that it hardly is reduced in terms of a capacity. For example, understanding of language and speech, it's best to learn at a young age, and then as one gets older, the circuits are less capable of undergoing any plastic changes. So there is some idea about being trained in ethical values at a particular age in order to follow the rules of both Chazal present and the quotes that William James has presented here. All right, so we now bring the concept of the brain. And so this then represents the contrast between the determinist and the compatibilist. That is, the determinist meaning that you're completely wired and an automaton with respect to free will. And as Francis Crick, the founder of DNA, who then subsequently went on to try to understand consciousness, put it, you're nothing but a pack of neurons. And so those neurons then can serve as the basis for determining exactly what your actions are. And in contrast to that, we have the quote, the psukim that I mentioned here from Bereshit, when God interacts with Cain, perhaps in an attempt to prevent him or convince him that perhaps killing his brother is not such a good idea. I've taken some liberties in the interpretation, but I think it's pretty clear that at this point that God is giving man free will. You have to make the right choices. Making the wrong choices come with consequences. All right, so what is the brain? What's responsible for our actions? So what I'm going to do for the remainder of the talk is describe to you some of the features of what the brain needs to do, some of the organizational features of the brain, and then actually look at a brain. And for those of you who are interested, this is a plastic brain, life size. It's wearing a bow tie tonight because I didn't feel like wearing one. Next week it will have some chocolate kisses associated with it. So here, this is the brain. It weighs, I don't know, 4 kilograms or something. So it's about typical body weight, not my body weight, but the typical body weight. It represents something like between 5% about 5% of the body weight and mass. Yet it is in complete control of all of our bodily functions, our thoughts, creativity, etc. So the brain comes in has 4 basic features. There's a sensory component that receives and processes sensory information. That sensory component then interacts with all the other 3 components. There's a cognitive one, there's a motor one that allows behavior, motor activity, and there's a state one which is involved with homeostasis, survival, reproduction, thirst, hunger, etc. All of these are interconnected through reciprocal connections. There are parts of the brain that are exclusively devoted to sensory. There are parts of the brain that are exclusively devoted to motor, moving our muscles and our limbs. There are parts of the brain that are exclusively devoted to making cognitive aspects to it. And there are small parts of the brain that involve exclusively with state, with homeostasis. But there are other parts of the brain where the immersion, the conversion, of these various components are not easily separatable. They're actually coexist in the same structure. The outcome of behavior comes in various forms. The one that's most convenient for study is movement, our motor actions. So we move in space. Our movements then are fed back to our sensory systems to make sure that we're moving properly so that we can make real-time decisions. For example, if we trip, we can catch our balance. Or if we're walking on straight ground or uphill, we change our gait, etc. Those feedback information is mediated through circuits that feed back to the sensory systems and start the loop all over again. In addition to this internal feedback, there is external feedback. We walk in the world. Our walking, for example, may not be appropriate. We may want to do something else. We can change our behavior as a result of our own observation of what we're doing. That has various names. They're called operant conditioning. They have various components, but relatively few animals can actually discern with the fine detail of how our interactions in the environment impact both on ourselves and with others. And that requires, again, a feedback association that results in activation of various cognitive areas of the brain. All of these components then interact in a seamless kind of way because we look at the universe and the world around us as being a single experience, but in fact that experience is fractionated into multiple components, which I'll show you a little bit now, and then reinstated to form a seamless whole. So you saw those in the previous slide, you saw those arrows. Those arrows represent connectivity, connections that brain parts have with one another. And so parts of the brain will become active. We'll talk about that in a little bit. What kind of activity activates certain nerve cells. That activity then is then transmitted to the next stage through a series of structures called synapses, where a transmitter, the chemical is released and activating a receptor on the postsynaptic neuron, the second neuron, and then leading to the generation of unit activity, which I'll show you in subsequent lectures, that are responsible for, quote, brain activity. Both of these sites of neuronal function, that is the synapse itself, or the conduction of the unit activities in the neurons, are subject to modification through learning and experience. So you can get a given stimulus after a learning situation to now result in the increase or decrease in more neurotransmitter, or the reception of that neurotransmitter can increase in the postsynaptic neuron. So that would be one site of plasticity that is modulated with learning. And the second type of modulation is how much unit activities are generated as a result of the same stimulus. So you can get modulation of electrical excitability as a result of learning and memory. So the point about this is that these are dynamic changes in the nervous system. The degree to which those changes take place is complex, not determinate. It varies from individual to individual, and within an individual, it will vary over time. So there is a four-dimensional quality, and those of you who are interested in string theory, perhaps a 4 dimensions is a Kleinigkeit, but it's a significant component of the complexity of the nervous system, and thus makes it indeterminate in terms of the philosophical issues that I raised before about free will. All right, so this is the basic element of how the wiring of the nervous system takes place. And so what is the brain? So the brain consists of the central nervous system of the primate, in this case is the human, has 7 components. It starts off with the spinal cord, where sensory information and motor information is conveyed into the body and out to the body for motor activity. The brainstem, consisting of the medulla pons and midbrain. This is the area of the brain where, when damage leads to brain death, it is essential for survival, plus a number of other critical sensory and motor functions that I don't have time to go through. But one critical feature of this area of the brain is that it's a site for a variety of neuromodulating transmitters, most of which you know, because you know about things like depression and schizophrenia and Alzheimer's disease. All of those neuromodulators are synthesized by clusters of cells within the brainstem, and these nerve cells distribute themselves throughout the brain and modulate the activity of the entire brain. And thus, understanding how those group of neurons behave with their complete interactions with one another, again leads to a significant level of indeterminacy with respect to the notions of free will. And then the next structure here is the cerebellum. It's important for motor planning and the conduct of motor activity. The diencephalon, which contains structures called the thalamus and hypothalamus, are critically involved with the processing of sensory information and motor information, both in stored as well as in real time. The hypothalamus is the small part of the brain that basically controls all of our endocrine and autonomic functions. And then, of course, the large cerebral hemisphere at the medial surface. As you can probably see, this is an MRI image of the brain. Here's the nose, here's the back of the brain, here's the spinal column where the spinal cord is located, here's the skull, the meninges are located here. So the cerebral hemispheres then represent a significant portion of the brain. There are, in the entire central nervous system, there are 10 to the 11 or 10 to the 12 nerve cells. That's a lot, a million cells, plus or minus a factor of 10, but you know, who's counting? I think Leo Flato asked me, how do we know this? And I told him, that's what graduate students are for. And on the average, a neuron has about 1,000 synapses, so that gives you 10 to the 14th to 10 to the 15th synapses. So this is a very complex organ with lots of things happening simultaneously and changing over time, and thus to be able to just say that we can determine complete cause and effect relationships of this structure is still way beyond the pale. Now, what are some of the functions of these parts of the cortex? Well, about 200 years ago, Joseph Gall discovered through palpating different parts of the skull and determining you know, if there was a Jewish person, certain areas of the brain would be much larger, like greed and things like that, whereas you know other people would have smaller areas. I mean, anyway, so he has. So there are things like love of the magnificent, acquisitiveness, appetite, combativeness, secretiveness, cautiousness, love of praise. Very small. Consciousness is up here. You know, some of by chance alone, he got some of the parts right, etc. So it's fun to look at this, and this was actually taken seriously for about 100 years. It also led to all kinds of ethnic issues that persisted into the 20th century, needless to say. We've come a long way since that, but the basic principle, however, is there, and that is that the brain, even though each one of our brains is different from the other, including this one, there are very specific, stereotypic regions of the brain that are involved with specific function. Now, you don't have to memorize this. You know, it's not like I'm going to give a test. Perhaps I will. But the point of this is now the cerebral cortex. It's looking at the left side of the brain. Recall that the brain is lateralized, so speech, for example, is found on the left side, not on the right side in most people. But there are areas of the brain that are specifically involved with things that you and I can relate to easily. So, for example, this region here in the parietal lobe. So let me first give you the lay of the land. Here's the front and here's the back of the brain. This is the frontal lobe in front and to the left of the red line. This is the parietal lobe to about here. This is the occipital lobe, where vision takes place. And this is the temporal lobe here. And if one were to pry apart the temporal lobe and move it downward, and the frontal lobe and the parietal lobe upward, and poke your finger in, you would see a valley, and that part is called the insular cortex. It's going to come up in our discussion in subsequent lectures about areas of the brain where when Bill Clinton says he feels your pain, those are specific areas of the brain where he in fact doesn't feel your pain. If he really felt your pain, it would be in this area of the brain. If he pinched him or something like that, that's where he would feel the pain. But when he just feels your pain, it's in other areas of the brain. And we'll discuss that in subsequent lectures. But, so the point is that there are very small, relatively small amounts of parts of the brain that deal with motor, specifically with motor activity, moving different body parts, feeling or mechanosensation, touching, feeling touch in various parts of the body, seeing the visual world, right, hearing the visual world, okay? But everything else, other than those areas, everything else is involved with cognition, with cognitive processes. It has a generalized name. It's called association cortex. It's a kind of throwaway word where one really doesn't know what it really does, but it does everything. But we don't know what everything is. But over time, as a result of people with strokes and have lesions, one begins to now discern what the specific functions of these areas of the brain are. So we know, for example, that this area of the brain is involved with speech. It's involved with syntax. This area of the brain here is also involved with speech, but it's more semantic, what words actually mean. Whereas here it's the grammar, the logic of speech. This frontal part of the frontal lobe is executive, making decisions, both moral decisions or inhibiting one's actions is regulated by these areas. But when one says regulated, one doesn't really mean absolute control. All of these areas of the brain are connected more or less with every other area of the brain. It's just that the preponderance of the activity associated with this area of the brain suggests sort of a specific function, but it's not exclusive. It's specific but not selective in that regard. So this is on the lateral surface of the brain. So although Gall didn't have everything right, but basically there is a consistency. So when a patient comes in with a stroke and they can't move a body part, it's because this part of the brain has been lesioned. And it's always going to be in that part of the brain. It's not going to be over here. It's not going to be on the undersurface of the brain. So there is a stereotypy in terms of the functionality, and this is a function of both the genetics as well as in terms of the size of the different and the slight variations is a result of postnatal experience resulting in the plasticity with the brain, of the brain. So when they kept Einstein's brain, and it was recently found, I think it was this area of the brain, approximately this area of the brain, where speech and spatial awareness was particularly large. Anyway, so okay, whatever that's worth, you can go on the subject. Cocktail party, say something. Here's now that medial surface of the brain. So remember, the brain has two hemispheres, a right side and a left side. It's connected by this tract here. Names are not important. And again, you can see there are some specific areas that are involved with unique sensory or motor function, right? Some sensory function here and here, some motor function here, but there's large areas of the medial surface of the brain that's involved with dealing with emotions, emotional memories, for example. And here we have parts of the brainstem and the cerebellum that I'm now going to just discuss for a couple of minutes because of its importance in subsequent lectures. This area of the brain is called the cingulate gyrus, and it's going to come up prominently along with the insular cortex that I mentioned before when we discuss empathy and other forms of altruistic behavior. Just a word about organization. The human brain, the primate brain, is highly fenestrated, lots of curves, as you can see from here. The foldings go in and out. That's to increase the surface area, and the reason why that's important is that the nerve cells of the cerebral cortex are all located on the surface. So you increase the surface area, you increase the number of neurons. Everything else that's underneath are the connectivity between the different areas of the brain. So that accounts for the large size of the primate, in particular the human brain. Now, some of the structures that I didn't show you but are going to appear and be important in our subsequent discussions relate to these structures here, and I'll show you on the next slide where they're located. I discussed already in the previous slide the diencephalon, which is comprised of the thalamus and hypothalamus. The thalamus is the gateway of all information that ultimately gets to cortex, with a couple of exceptions, which I won't go into now. Processes sensory and motor information to and from the cerebral cortex, and it integrates both current and stored information. The hypothalamus is important in regulating the endocrine system and the autonomic nervous system, and thus it shapes behavioral responses associated with survival, reproduction, and emotional behavior. The basal ganglia are an internal group of nerve cells. Most of you are familiar with it because lesions of the basal ganglia give diseases such as Parkinson's disease and Huntington's disease and various other diseases that are both have motor component as well as mood and cognitive issues. Basal ganglia, as we'll discuss in the next lecture, is critically important in goal-directed and motivated behavior, and it plays a very important role in addictive behavior as well as habit formation. The amygdala is a very small structure in the temporal lobe. It is basically the fear and pleasure center. It stamps all experience either in a fear or pleasurable or even neutral way, and thus contributes to a whole repertoire of behaviors that are associated with those situations. The hippocampal formation is important in declarative memory and navigation. It is the structure that is first lesioned in Alzheimer's disease, so early onset Alzheimer's has problems with this. Those of you who saw the movie Memento, that is what's going on, where the person lives in the present, cannot form any new memories. Everything is locked in the present. And in the third lecture, I'll be discussing the famous case of H.M., who died a couple of years ago, and was a subject for over 50 years, something like 55 years, where he had, because of epilepsy, his hippocampal formation was removed, as well as associated structures, and he basically lived in the present. He had memories up until about the age of 8 or 9. The surgery took place when he was a young adult, around 20. He survived into his 80s and was a subject of many studies. And the last thing are the brainstem modulatory systems. These are clusters of cells in the brainstem that release things like acetylcholine, dopamine, histamine, norepinephrine, serotonin, neuropeptides like opioids, etc., that have widespread action within the brain. They're critical for mood, goal-directed and motivated behavior, learning, habits, addiction, and homeostasis. So these are the parts of the brain that are doing their job without our cognitive awareness. They're doing it daily. They're important for survival. They motivate our behaviors to a large degree. Do we have free will in those respects? If you were to see something scary and your heart rate went up and your hair on the back of your neck stood up and you started to sweat, could you control that? Was that something that you really wanted to do? These are behaviors that the body does for survival, and they don't want you to cogitate about this. They want you to run away or fight or do something. They're not interested in waiting for you to think about whether this is a good thing to do or not a good thing to do. In other words, most of what our brain does turns out to be reflexive. What I'm going to say 3 sentences from now, I haven't the foggiest idea. All right? But I have a feeling that it's not going to be incomprehensible to you as a listener. You're going to hear me saying it, and you know, whatever you get out of it, you get out of it. But 4 sentences ago, I didn't know what I was going to say now, but am I completely out of control? Is that an act of free will? Is my speech to you an act of free will? If I reach out and grab this brain, this action of grabbing it, am I thinking about every action? Notice how my hand opens up before it. If it didn't open up and I just went like this, it would just fall off the table. So these are acts that we do every day. We don't pay much attention to them, and the reason why we don't make much attention to them is because our brain is doing it for us. So what about real decisions? Are real decisions, is that also being done by our brains, or are we contributing? Are we, is the individual, the subjective I, is that contributing to that? So those are the kinds of issues that I'm going to be discussing in the next lecture and the lecture after that, with this as a background to the kinds of things. So when I mentioned throw out a name, at least you've heard it before. You may not remember it exactly, but at least you've heard it before. And I'd like to thank you for your attention.
I have one question. There's a map for various parts of the brain. It's interesting, but of what use is that knowledge? In other words, suppose you know the area of speech, and you have a speech problem. Knowing the area, you can sort of start operating, or?
I'm not a neurologist, but one of the interesting things about damage to the brain, unfortunately, at this point in time, is that we're very expert in our diagnostic skills. We're still quite limited to what we can do to help the human condition. And one of the reasons for that is that unlike many other parts of the body that have the capacity to regenerate, the brain, there are only very few areas of the brain that show that capacity, the central nervous system. And one of those areas I'm going to talk about in the third lecture because it has to do with the area of the brain that is important for memory formation. So new neurons are born and contribute, integrate into the circuitry, and they themselves are the holders of new memories. So, and that continues throughout the life of the individual.
Two questions. Then one, in terms of this free will dimension, is it really doesn't this be an all or nothing ball game? In other words, couldn't one argue that there are cases we have free will and there are cases we don't?
I mean, that's basically going to be my punchline.
Secondly, if you adopted, as a rule of thumb, what might be called the anti-free will approach, is there any respectable Jewish theologian that would find that at all compatible or at all harmonious with Judaism in any sense?
Well, it's hard to make it harmonious with not just Judaism, but with any religion. No, at least in my mind, there is no compatibility in that regard. So if you're an extreme determinist, then there is nothing compatible with any of the religions.
Where Calvinism
yes. I mean, except for the religions who claim that it's determined, everything is determined. Right. So everything is determined. Yes.
When you talk about the fact that the body, mind,
will react to certain things. But at some point, it didn't. So at one point in development, wasn't this fear of fire or of an animal or something that was learned? So that what you're saying is that after you've made a judgment, or after you've formed an opinion, that becomes automatic later on? And would the same thing apply, let's say, to values? If you adopted a value because of something that happened early on, and that value keeps reappearing, isn't that something that's learned?
You're asking about 5 questions, so I'll try to answer them in the order that I can remember them. The first part is an interesting point. In other words, what is one hardwired at birth, and what does one acquire as a result of experience? That's debated in both the neuroscience community and the cognitive community. But it's clear most people agree that we are hardwired in a very specific way as a result of our evolution. So the areas, for example, that are devoted to speech are in fact genetically determined. For example, there is a family in the UK that has a mutation where certain individuals in that family are incapable of syntactic speech. So it's like they did not sit down and learn dictum. They just don't know how to put a sentence together, and it's a result of a mutation in a particular gene that has some human quality. In other words, it's different from all the other homologs in other species, like the monkey, for example. It's significantly different. There's a key difference in that gene. So, and it's believed that might be hardwired into our brains before we actually experience it. On the other hand, experience itself, as I showed in one of the slides, there are certain things that we do that have a critical period. If you do not do those things during the ages of X and Y, then you're going to have significant deficits in that functionality. So if you don't learn how to talk, right, you live by yourself or only hear animal sounds, then you'll never learn how to talk, even when you're now placed in a talking environment. So there are critical periods when one has to then have that thing. Now you raised it, then the next point is, well, can we extend that thing, which it tends to be more of a sensory experience. In other words, our sensory systems need this experience during critical periods in order to develop. Well, how far does that extend? Well, that's a great question. We don't really know whether different kinds of things have critical periods on a cognitive level. Like, when do you have to learn mathematics, or what about music? Those kinds of things may have very different kinds of critical periods, or they may not have them at all. So that's not known. So then, now let's do to the next level about value judgments, in other words, moral decisions and things like that. I would argue that too probably is hardwired because of our culture. In other words, culture selects for certain individuals who would then succeed in that culture, so it's feedback regulated. And so I wouldn't be surprised if certain kinds of moral decisions are also hardwired into the brain beforehand. So even in the absence of any experience, you would make the same kind of decision, even though you've never experienced it before. And if you took 10 different people, they would all make those same decisions that they never experienced before. But on the other hand, there may be a way during a critical period to make moral decisions in such a way that this would be how one behaves. Just like any other, if you can habit form moral decision making, you may then get a very nice society. Whether we had free will or not is another issue, but for the benefit of society, if everyone didn't go around shooting children in the school, we would benefit from that.
Just wanted to point. Does a baby's brain grow the rest of the body, or is it fixed at birth, the size
No.
of the brain?
No, there's a huge growth of the brain during the first 2 to 3 years of life. That's why, for example, the baby's brain, the skull is soft and can expand. Otherwise, it would be compressed and lead to all kinds of problems. So during that period of time, new neurons are born. Many connections, synapses are made. Many of them are lost and pruned in order to make a final system. Now, the specification of that system, as I'll show you in the third lecture, is unbelievably variable. Yet it still gives you the same function. To put the question another way, how much variation could a given circuit have in order and still give you a normal function? And it turns out that it's enormous. The variations are enormous. And the mechanisms that somehow regulate that are still being studied, but it's amazing how variable the specific details are. Which to me, again, rules out the whole idea of determinism, because any static picture of the brain that you can then use to explain a behavior, who knows what it was 10 minutes ago, or 5 minutes ago, certainly a year ago. I mean, it's impossible to know.
It's possible to know, doesn't necessarily mean that it's not. It may be deterministic, but it's so complicated.
By definition. Well, I gave 3 definitions. You're self-aware. You can respond to internal and external stimuli, and then you know what you're about to do because you've had choices and you have the intention of doing something.
Was the individual who had the epilepsy surgery, would he have been was he self-aware?
Yes.
Meeting your definition?
Yes, he was.
He was.
Sam?
Norman.
Come to Joe, wonderful talk. I've never heard it so clearly, precisely stated. In terms of the brain's development, it grows enormously, but one of the reasons that I think even the Supreme Court has said that capital punishment in many states can't be imposed, I think, under somebody under 16, is that the human brain isn't fully cooked until 18 to 21. And that was one of the reasons that the Supreme Court in many states have said that a juvenile can't be executed. I think 18 is the age. Because in terms of development, it's not fully grown until
Fully grown, of course.
yeah, by some, I think the AMA, the Neurology Board dictates. So it grows maximally until 2 to 4, but it's not fully developed until 18 to 21. But the other comment was in philosophy of mind and metaphysics, there's a school that talks about compatibilists. They don't talk about free will versus not, but they talk about compatibilism. And there is a tradition, including in ours, the Raub talks about in a book called The Emergence of Ethical Man, that he talks about constrained will, or constrained free will. And that's, I think, the model that you're developing. I'm not an expert in Jewish thought by any means, but in Musser, by choosing, the feedback model you gave is a very good one. By choosing a certain path, you alter the system. And then by modifying the behavior, one can alter one's behavior. Is that free will? Maybe, maybe not. But an organism, by making micro choices, can alter its behavior, human or otherwise. My last point is that in terms of what is consciousness, you gave as good a definition as I've heard. But in the philosophy of mind, Chalmers, who's one of the leading theorists, divides the problem of mind into what he calls the easy problems of how do we perceive red, how do we perceive color. Those are the easy problems.
And then the hard problems is what is the nature of consciousness? And that is what modern neuroscience is stumbling about. Self-awareness, the nature of mind. That's the tough problem, and nobody has come out with the clearest definition. It has to do with self-reference, awareness of oneself. It's been with us since Descartes, but that's what everyone is struggling with, because that's at the core of free will. When you can define it, then you'll solve it. Maybe by your third or fourth lecture, you'll get the report.
You know, it won't be solved. Oh, yes, yes, all right.
How does instinct fit into this picture? Or is that not a professional word?
No, it's, I mean, it's used more in animal studies, but, you know, but that would sort of be, you know, innate behavior.
Hardwired.
Which is hardwired. For example, this is just a personal observation. We had a bird for a couple of years, and you know, it lived in the house. It didn't know from any chachmas. It saw people. And one day, our friends brought their dog over. Never saw a dog, but it lost all of its feathers in about 3 seconds because it all over the cage. Never had. I was sorry for the bird. You know, I exiled the dog for a couple of years. And so these are innate behaviors. We are innately afraid of, instinctively afraid of snakes. And it doesn't require any previous experience. You are afraid of snakes.
So maternal feelings.
Well, I'm going to get to maternal feelings because that is sort of the harbinger of empathy. And that is contributed by specific hormones at a timely, in a timely way acting on the brain so that mom and baby bond appropriately, etc.
So it's instinctive and
Right.
also.
We all, whenever we see a baby, we all say ah and ooh and ah. And the reason that people give for that is that small heads, big heads, relatively big heads on small body is sort of a definition of cute. And so, when that, I mean, it has its limits, of course, for certain individuals, but you know, that basically is an innate behavior, and so there are many of those kinds of things, and they're hardwired. So again, you know, that's how we respond to it. It's like your doctor, you know, tapping your patella. It's a reflex that you can't do anything about.
So what does innate mean, though? I mean, might it just not mean that sometime eons ago we learned to have a hatred of snakes because of something that happened? I mean, if there's no stimuli to bring to cause that learning in the human being,
It doesn't require any learning.
so what does it represent? We're biased against snakes?
It represents a genetic wiring of the circuit that when it sees something on the ground that's thin and curly and moving, to fear it. And if 1,000, you know, 5,772 years ago, you happen to not fear that snake, your genes would be lost.
My question maybe is a little too late to go into that.
Thank you.